how many of you are familiar with the actor model? All right, very cool. So you're in the right talk. So the reality is that this talk really is meant to cover the actor model. Okay, I will use F# as a tool. I like F# as a great language. I like functional programming. But the reason that I really make this presentation actually is for some specific feature that I'm going to show you that only F# has. So, but you can do pretty much all that I show in other languages. So how many .NET developers here? Well, everybody. All right, so I think I started here, a lot of material to cover. So, all right, so hello everyone, thank you for coming. My name is Riccardo, and here today I'm talking about the actor model. As I mentioned, this is not a talk for F# per se, although I really like the language, and there are some characteristics that really make the combination between F# and Akka.NET a very shiny and bright combination. So the agenda for today, I will cover a little bit about what's going on out there. Really, our code is evolving. And then, of course, we're going to talk about what is the actor model. Briefly about the F# agent as a built-in agent F#. But the reason because I want to spend a few minutes here is because sometimes actor and agent are two different terms, different meaning, but they're used in the same context. So I just want to say, this is the difference. And then we discuss a little bit about the Akka.NET with the F# API. And of course, we're going to jump in a code sample. I really try to keep a balance between 30-minute slide and then spend the rest of the presentation in code. But really, some important theory behind this presentation I want to cover. And all the material is already in GitHub. So I'm going to give you the link in the hand so you can download it and play with. So briefly about me, that's the boring slide. But so I'm originally from Italy. I relocated here 10 years ago. And currently I live and work in Washington, D.C. I have more or less, I think, 18 years experience in professional programming out of the college. I'm an organizer of the C# user group. So if you're in the area, all of you have an open invitation. I work for Microsoft. I currently authoring a book for many publishing. It's functional programming in .NET, which actually all the code sample will be in C#. Because overall, functional programming is just a paradigm, right? So you can write in functional style with any sort of languages. And again, I really believe in polyglot programming. I really like to play with languages, right? All over, look for the shine and the lightest. So I will cover a lot of material, but these really are the three main objectives I want to take away today. Firstly, today, as never before, application must be built with concurrency in mind, and possibly in the beginning. And I've been involved in concurrency for several years. And really, to me, I'm a bias. I think it's the best. But definitely, the actor model per se provides a great concurrent programming model. That really is the key to scaling up and scaling out with the same exact API. And the combination Akka.NET and F# really a powerful combination. I'm very excited. In the end of the demo, I call the grand finale, the code sample that I really hope you're going to go home, download the code sample, start to play with this technology. So in the last really 10 years of in our field of computing, we see a dramatic change, right? Today, really, the demand for distributed system has exploded. Our user, our customer, a high expectation, one application responsive, no failure, and possibly, always run with the same performance. And with this demand, the requirement, also our way to write programs change, right? If you search right now online for the hottest technology, you find, cloud computing, of course, React application, real-time notification, SignalR, and so on, and hopefully all combined with big data world. Like everybody likes to talk about big data. So if you write this kind of application and still fulfill and satisfy this requirement, like scalable application, reliable, composable, and concurrent, is not easy, right? So what kind of tool and technology as a developer like me and you, we can use to achieve this goal, right? So these are a few quotes of a book online. And what really mean to me, really the landscape of distributed cloud computing has expanded, exploded. It represents a dramatic change for us. But the reality is that today we still try to figure out a good solution to defeat the multi-core era, right? The fact that we are still facing and try to defeat this problem, the multi-core era, well, in the same time, we have to try to write application in a distributed system. So it should be nice to have a technology that actually satisfy and able to provide us a tool to defeat both issues, right? So, and over this question issue, there also derives a solution, right? This is one answer, right? The Active Manifesto. How many of you familiar with the Active Manifesto? So really, the Active Manifesto is the answer for what I just showed in the last two slides. The world is going reactive, and the Active Manifesto per se is just a paper that represents a set what kind of characteristic the application must meet to satisfy this model. So briefly, responsive. Well, you can imagine just a system that it will work in performance in the same way, no matter how your server is under stress, no matter how many requests they receive, right? Message-driven is more like an architecture for loosely coupled and asynchronous, no blocking. Is really the key for scalable application. As you can see, more and more trend in mainstream languages like even C# start to use the sync word and so on, right? Because this is a problem to solve, like asynchronicity and scalability. Resilience. This means that the system is able to self-heal, right? Is able to. There is a problem, right? Something goes wrong, right? Sometimes, but the system is able to isolate the problem and react accordingly, bring back the system in shape, right? Really a self-healing system. And we want to discuss about this part with actor model, that a way to achieve resiliency is really embrace failure, right? And elastic, this is the key for distributed system. Elastic means the system that is able to expand on demand and contract on demand too, right? It's able to add more node on the fly accordingly to the request, but also not just scaling out or scaling up, but it's smart to scaling down, right? So this is a slide that I think in the last 5 years at least, all of you saw, right? But I like this representation with the color combination, really represent better feedback. But really, the trend of the number per core versus the speed per core intersect here. You can see the number per core keep going, right? So in 65 Moore's law predict that the density and the speed of the transistor were doubling every 18 months. But we almost reached the speed of the light. It's not possible, right? So company overcome this issue just providing and shipping hardware with multiple cores. So today, really, we need a good concurrency programming model. I think everybody that cell phone with more than one core in your pocket, any kind of device has more than one core. So there is this evolution of hardware toward the multiple core. So the reality is that programs no longer can leverage one single CPU that gets faster and faster, right? Instead, we really need to be able to parallelize and leverage all the resources that we have. So the free lunch is over. I don't know if you read this paper, but so really, what does it mean? That today and more in the future, the company will ship multiple core hardware, right? Which is great because it enables us to write applications that can process multiple tasks at the same time. But it's not easy, right? Languages, traditional languages, mainstream languages like C# and Java and so on, weren't designed with concurrency in mind because at that time, it wasn't an issue, right? So it's not easy. So you run your application today, you figure out, well, yeah, I have one hard worker, right? And all the others are just looking around. And these guys, they all go in the same speed, right? 0. So, all right. So your boss came along and said, well, make it faster, right? All right, no problem. Multiple thread here, span around, everything looks easy in theory. But we know that in practice it's a bit different, right? So what's the problem? The problem is shared state, right? Is commonly acknowledged that write concurrent application is hard, but even harder is write correct concurrent application, right? You like the two threads to catch each other? That's pretty nice. But so in a multi-thread environment, if you're careful, you have this kind of problems such as deadlock, race condition, and so on. So the problem is really the shared state, and what you can do to avoid that? Well, you start to use primitives such as mutex, semaphore, locks, and so on, which can work, right? But there are a couple of problems with that. First of all, there is not really any compiler tool, debugger can tell you, well done, you put the lock in the right place, right? So maybe it works in your machine, right? But your machine, I'm pretty sure, is not able to simulate exactly the same stress that your server production have, right? So you ship it, and after a week, you have deadlock, and your server is down. How can you reproduce that bug, right? It's not easy. So really, and besides, locking per se is just a bad word, right? Lock. It really prevents running parallel. What really does lock is really protect a state, a portion of code that is a state, to be corrupted. So it really prevents your system to crash. So if you in this case with the classic bank account, if thread red change the state of the account or the amount of the account in an unwanted state, well, thread blue is not happy. Maybe your system can crash or start to have unwanted behavior, right? So really, the shared state is bad. And also performance-wise, maybe you need the lock to synchronize and protect the state one call every 10,000 times. But the lock is there, right? It's being called every single time. So shared state is a big problem. Now, if you're familiar with functional programming, I'm sure you heard about it, that functional programming seems to be the solution. Oh, well. Well, the fact that functional programming is immutable per default, right? So it's a great support for concurrency because it removes the problem in the source, right? It's not shared state problem issue, right? So functional programming are a great tool that more and more you see mainstream languages adding features in other languages that try to be more functional, right? And must be a reason. And functional programming per se is not that they run faster, but they're ready to be parallelized, right? So really with small change in your code base, your application can be parallelized. Now, immutability really is a great solution. To me also, natural isolation is a great characteristic that make your code great for concurrency, right? So this is F# agent, so don't worry too much about the syntax right now, but bear with me. So here we have an agent, how to implement an agent in F# that accepts a function. And this is a recursive asynchronous loop. Here is waiting for a message asynchronously, no blocking, right? There is pattern matching, deconstructing, do something. But really what is important in this line here. So if you're a .NET developer, dictionary is a mutable collection, right? So some sort of cheating here, right? Because I just said that functional programming is immutable. Why should I use a mutable collection, right? Well, it's isolated, right? I'm inside an actor agent. So nobody can access this state. It's protected. So it's okay cheating, right? Anybody familiar with this Amanda's law? So we just found the solution for concurrency, right? Immutability isolation. That's great. Well, this guy wake up one day and say, nope, sorry, I make your life harder. What this guy said is that no matter how your application can be parallelized, the fraction of code can be only sequential. It's going to jeopardize the overall performance of the application. Like for instance here, if your application can be parallelized for 95% of your code, you're going to reach the limit anyway, so 20 times faster. That's it. No go over. So this is a problem, but it turned out actually that the actor model deal quite well with this problem, right? Because actor model really promote intercommunication between processes and computers to really cooperate to achieve the same solution, right? So I'm talking really distributed system, because at this point, yes, it's 20 times faster limit, but it can be how many machines? Really unbounded power, right? And now bring us to the actor model. Anyways, any questions so far? All right, so the actor model really independent computational unit. Really, it composed of three parts: a mailbox, which is our queue, our state, and a behavior. So what it does, the actor model really is single-threaded, right? So that's all. That's the trick. So you send messages that is unblocking for out the world. Like I keep sending messages asynchronously, and I'm done, like fire and forget. The actor receives the message, react, and with the behavior, process the message, right? Is applying the behavior to the messages. And again, can be at some state internally. And all the other messages income, right, they're not lost, because when the actor is busy processing a message, all the rest of the messages are just buffered, right? So really think about the actor model as a rental car, right? You need a car, you go to a rental company, you drive around happy, the car breaks, right? You don't care to fix it. You just call the rental company and they send you a new car. This is what really, to me, means an actor. Any question about this slide? And again, I want to point out that the state is isolated, right? Really, the actor are this share nothing approach, right? When you send a message, actor really have support for both immutability and isolation, right? Forget for 1 second that we're talking about functional language, but messages are passed by value, right? So the actor model can be implemented, in C# or Java, that they are, mutable languages. But messages are passed by value, so they're immutable, and again, they're isolated. So we're bonus here, right? Same system give us two great tools for a good, correct programming model.
So you're saying that it's like a rental car because the actor stops, you just have another one.
Yeah. There are different implementations. I'm not going to go in detail. I'm going to discuss about how Akka.NET work. There is other frameworks such as Project Release from Microsoft and so on. They all have a slight different approach, but the result is the same. And fair enough, the actor model is not a new concept. It's been around for a while, for over 40 years. These guys, Carl Hewitt, in 1973, wrote this paper about mathematical model for concurrent programming, right? And describe how you can write correct concurrent application using this mathematical model. So the actor has three axioms. You can see in the slide, an actor can send messages to other actor, can create more actor, or can determine how can react to the next received actor. Because yes, the actor have an internal behavior, but it can change behavior, right? Meaning you can send a message because the message has some special feature can change behavior. And one of the things that I want to point out in the paper said that one actor is no actor because actors can communicate by each other. To me, my experience, I found very useful to found application just one actor for the same reason that actors are great to build fine state machine, right? Maybe we're not still in concurrent application, but it's asynchronous, it's isolated, change behavior is a great tool, especially like if you build your own login system, right? Very fast, you send the login to the actor and just logging out. So there are different kind of possible usage for the actor. And one reason that it got even more track in these days, in these years, is this myth of the 9-9ers that Ericsson was able to reach using Erlang in the 80s, right? Are you familiar with Ericsson Erlang? I think at least you heard the name, right? So Ericsson, of course, is in the telephony industry. And in the 80s, built this switch, telephone switch, and used Erlang, which is a language that they built in their laboratory. And they used the actor model, right? And they embraced the failure, the let it crash approach. We discussed that in a second slide. And with that, we're able to reach the 9-9ers, which means 30 milliseconds down per year. Now, if you make some search online, you see, because I was curious, how was able to measure this, right? 30 milliseconds per year, what? So actually, if you read the paper and make some research, it turned out that actually was 5 9ers. Sorry, disappointed. But still, 5 9ers per year is 1 minute and 20 seconds down. Pretty cool. But ultimately, more important, really, the actor is completely full compliance to the reactive manifesto paper we had, right? So again, the world is going reactive, so go with the actor, right? If you have the actor responsive because it's event-driven, use asynchronous message passive semantic to communicate between each other, so it's message-driven. Of course, it is resilient and elastic, and we talk about these two parts coming soon. So briefly about the agent in F#, and I said in the beginning that I want to talk about, I have 2 slides and a half about F# agent, and the reason because I want to point out the difference between agent and an actor. So F# has a great support for concurrency. I have the async workflow. I'm not going to spend time there, but mailbox processor is an agent, right? You can see exactly the same component actor, mailbox, behavior, state. So what are the different, right? Well, if you check the code here, right, that you create a mailbox processor agent, there is nothing wrong here, right? They have a loop, receive a message, pattern matching, deconstruct my message, and process it. Very simple. But there is a problem with this code. It's not a bug. The problem is part here. And the problem is that you can access an agent only through an explicit instance. Right? What does it mean? It means that an agent is in process, can only be in process. So, and it turned out actually that agent being in process only, actually provide a more functional approach. And the reason because think about the agent is a memory slot, right? So it's not that like an actor, you can send state to a behavior versus an agent, you can send behavior to a state because it's in process. You can even send function, right? And even better, you have this function, compose the function to a more complex one, send it, and then apply atomically to all the bucket, to all your messages. So this is the primary difference between the actor and an agent. The actor can also be distributed. Agent is all in process. Question about this part? All right. So, and let's bring it to the Akka.NET, which is really the port of the popular Akka from the JVM ecosystem. And they actually, this is their definition, right? They define really like a toolkit that is used to build systems with better performance and in a simple programming model, right? And actor in Akka are very cheap, right? We can fit 2.7 million actors per gig, which it seems absurd in the beginning, but actually it's a great power. You can even model all your domain with actor. And they're so cheap that you can just create actor just to solve small, simple issues. So we're going to see an example later, but I think the fact that they're so cheap, you can create actor that control other actor, and that's why there is also, if the actor crash and go down, they create another actor. I mean, it's a very powerful concept. So how are we going to achieve this number, right? Well, the reality is that the actor is reactive, meaning that when it's idle, the thread that owns the actor is sent back to the scheduler, to the thread pool, right? And when receive a message, then you react. and the thread come back from the scheduler and process the message. So let's talk about supervision, right? So how do we keep our system from falling apart when things go wrong? Because things go wrong, right? Well, the secret is supervision or parental supervision, because really the concept is that actor create other actor, and they create this relation, become a parental relation, right? So how can the supervision resolve the error, right? So there are different kind of approach, and we have briefly 2 slides about that, but you can build your own. As default, you just restart the actor, but there are many different kind of approach. You can inject your own. You can resume it and so on. And really is able to, according the exception that is raised, you can inject your own custom behavior. But what is important about this? Let it crash, right? I mean, I'm sure, like, I'm one of these guys that is very particular, right? I mean, I'm maniac about my code, try catch here, try catch there, log in all the time, be sure that nothing crash, right? Well, guess what? The truth is that no matter how paranoid you are with your code, they're gonna crash sooner or later, right? Maybe they can lady unplug, the power that happened, every night at 3 o'clock for some reason, the server was down. Nobody knew why. Well, we figured out the problem. So really, let it crash, embrace it. How easy it is, right? So, by the way, very interesting. Erlang start, in '80 with the actor model, and actually, it's interesting how they start to use some terminology that's been coined and used today is used for other framework, right? So even the supervision here, they start to call it one-for-one supervision, and now all the framework use the same concept, which is pretty interesting. But anyways, one-for-one supervision is the fact that if you're a tree node here, right, with all these actors here, with the main root there, if one actor goes down, well, the system is able to react and bring back in shape the system it was in the beginning, right? Instead, that one-for-all supervision, well, if one node goes down, the strategies apply to all the node, all the siblings that belong to the same node, right? All right, so remoting. And remoting is really, Akka is designed for distributed system, right? Is actor model. And remoting the key for distributed system. You really, you need to know, you don't care when you send a message if the actor is local or remote, right? And the great part, thanks to remoting, you use exactly the same API, right? So it's completely transparent to the user. So provide this unified API to send the messages to actor can be remote or locally. And this concept is called location transparency. Meaning that whenever you send a message to an actor, you don't care where it is, right? Think about if my wife is looking for me, I want to send me a message, she doesn't need to know where I am, right? Here in Florida, Washington State, whenever. She pick up the phone, she knows my phone number, she send me the message, right? Exactly the same concept. So that's why also the difference between agent and actor, right? They call actor ref, but there are no reference. They are really address. And they're smart enough to realize if you're in process, they use an instance. Otherwise, they use an address for a remote system, which is pretty fast. And this is really the secret for able to scaling out and scaling up. Because at this point, you can solve the multi-core problem because you have multiple actors in your system, you send the messages. And maybe the system need to expand, create more actors in a system, and you don't care where it goes, right? All right, but this is it. This is the money slide. This is all the point of this presentation. That's why actually I want to make this presentation. If you don't see much here, we have my grand finale example, as I mentioned. So I use this technology. So this is a feature specific for F#. It's called code quotation. And what it does, you create your code between the arrow at, and F# create a representation of your code, an abstract syntax tree. And in combination with the F# API and Akka.NET, you're able to serialize this code and remote deploy the actor to a system that have no idea how to implement an actor. You had the demo actually that I will remote deploy simple console application, something that doesn't exist, right? So it's pretty cool. It's almost like Erlang, right? So you can hot swap and remote deploy the actor. So that's pretty cool. But wait for the grand finale. You're going to be so excited. All right, routing. I'm going to go quick here. Routing really, the idea, there are different kind of actors. Core routers, router that are a little bit different than actor because they're faster. Like actor usually process one message at a time. Router can process more messages at a time because in reality they don't process it. They receive it and send it out, right? So they're very fast. So you can create router exactly you create an actor and just apply some optional parameter to how apply this strategy. And really the idea behind routing is that you're able to distribute your work, right? You can create manually your actor and group it together. At this point, router is an actor that sends these messages to these different actors. You can put in your configuration file, like the instance, create two. But documentation line is great. And there are other configurations that you can even set some threshold, like if the CPU reaches this kind of percentage, spawn a new actor in a different machine. If the memory usage in this machine is low and I need more power, bring a more actor in a local machine. So it's very powerful. And this concept can be stored in your config file, right? So there are different kind of strategy, but the most used is the broadcast. You can imagine a router receive a message and broadcast the same message to different actors. Maybe each actor different kind of behavior. This is the classic round-robin pool, right? This is great when you have create an even distribution, right? You send a message to the router and then distribute the work to different kind of actor. Round-robin group, this is like the combination of the two previously, right? There are different kind of strategies, such as, I forgot, I meant to look today, but it's like dynamic, elastic, I think it's elastic something. But that's that you can even R-code instead of the config, said, this is my threshold, create more actor if I need it, otherwise reduce it, right? Scaling out, scaling out. Scaling out, scaling down. Pretty cool. This is the last slide, and then we're going to jump in a code sample. So there are two different kind of actors, a type and untype. I think pretty clear what this means. But actually, you cannot see very well there. Well, anyways, the thing is that the Akka from the JVM, they're currently working this feature. And in the beginning, so why you want to have untype actor, right? Well, actually, it turned out that probably the most powerful. Because, like for instance, especially in combination with the F# API, you can change behavior, hot swap behavior internally of your actor, but you cannot change signature, right? You're going to break a lot of stuff. So usually recommended to have type actor that is really like a bridge between the outside world, like imperative language, call this method that really look like a method, type method. And behind that, you have the untype actor that you have more control over the implementation and hot swapping and so on. All right, so I think it's demo time. Any question? All right. All right, so I'm going to build up, right? So we have 30 minutes. So I think we're good. So I'm going to start very simple and then build up with remote supervision and then the graph finale that will be so cool. So I'm always glad. I know every time you see, I'm like, whoa. All right, so let's start implementing a simple actor. So you create your system actor, right? You give it a name. Let's create the system in your process, right? Because like Erlang, if you're not familiar, actor belong to one process. You can now have more one actor per process. Instead, with the Akka.net, you can have like a 3 actors in the same process, and can be different process in the same machine or distributed, right? This is a very imperative way to create an actor. Oh, wait. Yeah. So you inherit it from the actor here, which is untype, right? You have the function here on receive, and the message is an object type. So even a C# developer, I think it's pretty clear, right? Inheritance, a class. Type is a class in F#. Your implementation here. I check what type of message it is and process accordingly. Like here, how you create an actor. You create your system that I create here on line 12. And I reference the same system and create my actor type. And then I can send a message with tell or ask. And we're going to see what that. So let's create it. I use the repo. So the cool thing about F# is that the repo, right? So really you can select your code as long as you want, and you can send it to the repo and just analyze it in real time. Anybody can see in the back? Probably. Let's see if I... Better? Confusing? Enough? All right, cool. So now I can create my actor here. All right, so you can see here, I create my F# user, which is my actor system here. User is the root, right, the guard. No matter what's happened, it's called guard because no exception can reach the point, right? We're going to see, actually, you can put your strategy, but if you handle exception, if you don't want to handle it, can bubble up until you want to. But until this point, the user guard. At that point, if you don't have your strategy apply, use the default, which is just restart the actor. The B here is a $B is an arbitrary name of the actor. So if I actually give it the name which is recommended, right? I can create the actor now and with the name provided. So now I can send a message. So if it's a number, actually if it's a string, it just print hello. In this case, actually going to say hello twice, so remove this. Found a bug. All right, hello Akka is a string. If I send an integer, I use pattern matching here, and the integer doesn't know what to do. It can be integer anything, but I use the wildcard, the underscore. At this point, it just say I don't know what to do, print the type, right? So 42. Okay, very simple, right? Cool. Now I'm very excited, I know, but wait for the grand finale. All right, let's go to the increment here. So the increment is type actor, right? Oh, wait. Yeah, better. It's a type actor. So in this case, I create two type, which is, again, don't worry about the syntax in F#, right? But really, here is some sort of discriminator union. So is in F#, think about discriminator union as a collection of types that all are based upon the same base type. So increment, think about increment message as your abstract base class, and increment and print your superclass. Actually, oh, sorry, the class implement increment class. So I have two types, increment or decrement. I have my actor implementation here, which I use the receive actor. And you can see here, this has become a type actor, right? So a different function for this message type. In this case, I have increment message and decrement message. So when I send a message to this actor, depend upon the message type, the function get the message and process it. I use a internal state because internal state in an actor is safe, right? So very simple implementation. Just send a message, increment the state, which is a number, an integer, decrement, reduce the number, right? You can see here. Interesting this part, the type actor, you can even have like an handle message, which does exactly what untype actor does, right? You can, as default, for instance, you send a message that the actor don't know what to do with that, just got lost, like a dead letter, right? Or you can create this custom, you can override this function here, implement your own logic, maybe some login and so on, right? All right, so let's run all my Arapo. All right, so I create my system, okay, and now I create my actor, which is a more friendly way to, more friendly way to create your actor. Just specify the type in the name. So now I can send my messages, right? Print 0, we know the state is 0, but I also print out a console log, just say this is an increment message type, right? All right, so I can increment, let's see, twice. Now I can use the second type of message, decrement message, right? And print 2. Very simple, but now you have type actor, right? You can create a specialized function for the type. This left arrow bank is a F# API, function programming like to have cool, small syntax. You can create your infix operator in F#, and this is exactly do the same as the tell operator. I just want to put it there. So, any question about this part? Ready for the exciting part? How going by time? You haven't. How long is this? 10, 15? 20 minutes. Okay. Okay, so let's start with the F# way, right? So anyways, here the same way you create your actor type, discriminant union. So here is a bit different, right? System create versus actor system. System create is built in for F# specifically and support one of the many features, also the abstract syntax tree. In F#, we like functions, so we have this spawn function, the signature. I don't know if you can see here, but what it does is a parameter system type, the name of the actor, and a function that take the actor body, right? So spawn, I put my system, I create here in line 18, the name of my actor, and then my function. So F#, is a functional language, so we have a recursive function there. And what it does is just wait asynchronously for a message and process it accordingly, like great or great the name and so on. Here, actually in F#, how you implement different behavior, right? So in this case, the function is recursive. So I have two functions. Again, the pass state, which is a string type, and a loop, which is a second recursive function, right? Everything starts with the loop. So at this point, my actor starts, and this is the piece of code that is running. I send the message, I print out hello, and now I say, well, return, but start from the gain, passing the name, right? So at this point, the behavior of my actor change, and this piece of code is running. That's why I think that actor model is great for for fine state machine, right? So this example, just gonna print some name. I want to just show up a little bit the F# API, go with something a bit more sophisticated, right? Let's start with implementation of chat, right? So this is a 3 project plus an helper. So the messages here are just a bunch of, actually I don't need this for now, a bunch of type in F# with a member, which is like a class with a property, right? So pretty simple here. This is going to be my messages, right? Nick response, say request, connect, so on, pass a string with the username. So pretty straightforward. The server, I had some configuration here, and I bomb up all the login, right? So I have a lot of console, fancy color coming out, saying what's going on. I say to listen to port 88 in localhost, using TCP protocol. Use Akka.NET, use TCP as default and protobuf as serialization. You can use whenever you want. UDP, I think, is the second one, but you can inject your own and change serialization too if you want to. The system, so the chat server is really a a recursive function inside my actor that keep the state of my actors, right? Is a list here, which is immutable because F# function programming in general are immutable. So if you check here the first part, when I connect the request, I receive a connected request with the CR type, which is my message, contain a username. So I just create a response and send back to the caller. Inside the mailbox is able to detect who sent me the message, so I send him back like a ping pong, right? So now I get the sender and send back a welcome. I do some login here, and here this part, I just restart the looping the same function, just attaching the new client to my current collection, right? So it's create a new list. Second part here, just some printing and then broadcast to all the client. You see, all the client register, send a response here. So don't worry too much about the syntax, but just the high-level concept, right? So this is the server. The client, I'm just gonna ask for the user ID, username, same configuration, localhost, TCP. Now the interesting part, I have the address of my server here, right? So I can reference this, the chat server. And this can be out the process, different machine, I don't care, right? So at this point, I send messages to my current actor, my client, to the console. And when I receive a message, I'm going to send the message to the server, right? I just keep sending messages, and the server processes it accordingly. Can you tell me when, like 10 minutes before? You said 10:30, right? All right, 5 minutes. Okay, I can do it. So this is pretty much the client, right? And here is the console part that keep my messages and send it back to the server. Just simple console. Let's run it. I have this chat helper, which is a script that just pretty much run the executable for the server, the client, and actually I start 3 client because you don't want to talk by yourself, pretty sad, right? So, all right, so the REPL here, all right. And now I'm going to start the server. All right, cool. I have 1 client, 2 client. I don't care about this client. This is my server, right? All right, so username Ricky. I sent the message, so the connection, and the server said Ricky joined the chat, okay? Bryony, say hi, okay? They're both connected. And you see, send back the welcome message, right? So now Brian say hello to Ricky, and Ricky receive from Brian the message, and Ricky respond ciao because I'm from Italy. Well, pretty simple, right? But so simple create inter-process communication. Like this is a simple chat system, but pretty cool. All right, I think I'm gonna skip supervision because I want to be in time. I want to run 2 examples, including the grand finale, right? Come on, that's worth it. I mean, all right, so let's start with the remoting, right? Where was it here? All right, so the remoting, what I will do here, I have some configuration, localhost. Is this one? Yes. I create 2 function helpers, so don't worry again about the syntax. But what I do here is said, I have an option for deploy, right? I'm going to pass this function here, and I use the remote deploy, right? Passing the address. So again, I create my system here, right? And here I'm doing something super cool. I use the code quotation to create a very simple actor with a console. The grand finale is super awesome, but anyway, what to do here right now, I said, okay, by the way, who noticed I have a Mac here? All right. So I'm running Visual Studio in a Windows VM, right? This is my Mac machine. So I have 2 different computers, right? This is Xamarin. I used a a simple console application. It said the host name, the port, I do some log in the console, and here I just create a system with the name remote system. There is no implementation in any actor. If you go to the reference here, there is only about the package for the Akka.NET. So the system up and running, that's it. No actor there, right? So should be cool if able to deploy an actor here in my Mac from the Windows app. Should be cool, right? Let's see. All right. So I select all my code here. Let's reset. OK, reset. Select all my code here. And again, don't worry too much about the syntax. I'm sure after the grand finale, you're going to go home, download everything, and play. You're going to be pro. This is it. So I create my system. OK. Let's lock it here. There's nothing here, right? There is a remote actor, remote system listening. 10 minutes? Cool. Now, when I run this function, I'm going to use the span remote function that I just created above. It's a helper class, right? Tell it to remote deploy the actor with the name hello and this implementation. All right. Because it's not a trick, anybody can tell me a color beside magenta? Huh? Cyan. All right. Cyan. And the message received, your name? OK? All right, now I'm going to deploy the actor, OK? Deploy actor. If I go here, something happened, right? There's some sort of handshake in the, my student said, OK, I trust you. I get this code. Security is another topic. We can discuss after that. We can discuss after the talk, but there are some future about implement security. So I just, I'm a Mac. I trust myself. Sometime. So at this point, I can send a message, right? So I can send a message. So what's up in the console is nothing. You say, OK, the function has been applied, but there is the console result, right? It's here. Say, Jeremy, receive hello from F#. Cyan. Pretty cool, right? Wow, you're excited. I like that because now the grand finale is going to be all right. I like that. All right, so this is pretty cool, right? And you can create on the fly here, or swapping and so on. So there are other more code sample, but let's go to the grand finale, right? The grand finale, the fractal. So there are actually three code. One is C#, implementation of no judge, the Melbrot algorithm. So just going to get some numbers and produce a bitmap. So pretty, you know what, just blame somebody that posted in a Stack Overflow, OK? It's not my fault. So the fractal remote, exactly the same implementation that I had in my Mac, right? So I just create a system, and that's it, right? So the fractal here, that's where the cool part starts. So the idea actually going to tell you what's happening. We're going to go to the code and run it. What's happening is that I have a system here with no implementation or anything, OK? My fractal is a WinForm app with a big picture box. I'm going to slide in a little tile, remote deploy an actor with the Melbrot algorithm in the back. The remote actor receives this coordinated, create a small picture tile, send them back to my actor, and publish the tile to the picture and create the Melbrot graph. All right? Pretty cool. Wait. So this is just a WinForm setting. Don't worry about. On loading, I have my configuration part. I localhost, port 0, because I don't care where I listen, and because when the remote actor receives a message, send them back, right? You already know my port. I create my system. I do my setting for my picture box here, OK? So nothing, straight code, right? So I have two hyperfunctions here. with the bitmap, I receive an array and transform in a bitmap. And the render is just receive the byte array with the coordinated, use the previous function, create an image, and deploy and render to my current picture box. I display tile. So the current system have a local actor, display tile, that is waiting to receive this message from the other actor system with the array byte, because it relies the bitmap from the remote actor, with the coordinated, use the render function that I just created here, and render the tile to my picture box. And I use the spawn option dispatcher, so there are no like Marshall threading exception, because I can update my picture box for a different thread. Deploy remotely. I create a router, round-robin pool. So this is a more complex actor, right? So you can see here, this is the actor going to be remote deploy. I'm going to deploy my function, which is a C# function, and hopefully somebody make a question. I get create an array and send the array, which is the empty tile, to my remote actor, and that's it. The remote deploy with the router function here, right? Okay, so the sender here is my remote actor that I just deployed. No, sorry, take it back. This remote actor actually is the current actor. So when I remote deploy this actor, the sender, it will be this actor here, right? Can you follow me? Because this is going to be local. All right. So, and then here I just slice my picture in tile and send it to the remote actor, send the coordinated. That's it. All right, let's run it. Okay, I run the remote actor that again is just a poor sed console, no implementation, doesn't know anything. Okay. Now, when I run this code here, the fractal, I'm going to remote deploy the actor, start to shoot them tile, black tile, and receive it back. All right. So this is my remote actor, so there is nothing implemented here. I start, all right, so send the tile and receive it back. You can see here something's happening, right? This is the login to the remote actor that, all right? You understand what? That's pretty cool, right? All right. Now, thank you. Now, let's do better, though. And that's going to blow your mind. That was cool. But you know what? I'm not happy. How about this? How about said remote, you know what? I don't want an actor remotely. Create a router, 16 actor in the back, and shoot the images and make it faster. All right, so now I run it. All right. Now I run my fractal here. No, wait. All right. All right. CPU is going 100%, way faster. Right? CPU 100%, close here. Now, this is cool. I didn't touch supervision, which is cool, but anyways. We have 1 minute, 2 minutes, 1 minute. Well, why doesn't it run? All right. Best practice, okay. Pro and cons. Everything is a pro beside when you run in transaction kind of way, like you have like two-way commitment. Probably the actor is not suited for what you need, but otherwise, I don't have any cons here. I don't know why it's not expanded. All right, whatever. Summaries, build concurrency application from the beginning, and actor model really simplified everything. You have one API for both. Distributed, local, multi-threading, or distributed again. again, yeah, okay, we talked about that. Akka and F#, I proved that the code quotation and Akka and F# are just pretty awesome, right? So now, question, reference, okay. This is my GitHub. You have my slides there and my code sample. Hopefully, you can download it and play with Akka.net. This is my email, my Twitter account. Tweet, say something awesome. Otherwise, don't tweet. And this is my email. All right, that's all. If any question, let me know. Otherwise, I'm around here.